So for this section of external convection, I will need that you have handy your textbook because when dealing with tube banks, we need to use at least 3 different tables for solving for tube banks. So we will be solving a tube banks problem today. And this kind of problem is very important because it's related to heat exchangers. So anyway, I will show you the graphs and tables you need to use, but it's good that you start locating them and marking them in your books. So tube banks are very important for many applications, and it consists of more than one cylinder. Last class, we evaluate how to solve for external convection for cylinders with circular cross-sectional area and non-circular cross-sectional area, right? So now we are going to evaluate what happened with external convection when we have 2D arrangements of tubes that typically we call these 2D arrangements banks or bundles. So in this type of arrangement, typically a fluid flow over the tube bank and another fluid flows through the tubes, like in a heat exchanger, okay? Now we are evaluating external convection, so we will be focusing on the phenomena occurring when the fluid is flowing over the tube bank. Typical examples when we apply these tube banks or bundles are cross-flow heat exchangers, convective space heaters, and electric immersion heaters. Okay, so that's why this section becomes so important for us because it sets the basis for heat exchangers analysis. Okay, so again, we are putting several tubes together. As you can imagine, now that we have a 2D arrangement or bundle, everything changes, right? The temperature profile will change, the velocity profiles will change, right? Because you cannot evaluate only one tube. All of them are interacting, right? So all of them, there will be different profiles along the columns or the rows of the bundle. We can have different geometries of these bundles or 2D arrangements of tubes. And you have this figure in your textbook, figure 619, to show you how inline tube arrangements look like. In this case, very important, all the rows are aligned, like you can see, right? So we have aligned our rows. See here, your figure is showing the direction of the flow and some nomenclature, ST and SL. ST is the transverse pitch, is the tube spacing perpendicular to the flow direction. SL is the longitudinal pitch and is the tube spacing parallel to the flow direction. Okay, so that's nomenclature related to this 2D arrangement of tubes. And we will continue with this nomenclature when reaching heat exchangers theory. So SL is the longitudinal pitch or that spacing, again, tube spacing parallel to the flow direction, and ST is the tube spacing perpendicular to the flow direction, right? What is the flow direction here? Right, our flow nitrogen, CO2, air is passing here outside our tubes. And this is a common inline tube arrangement. We can have another common way to arrange tubes in 2D bundles. And this is the offline arrangement. So we have alternating rows are offset by 1/2 of the tube spacing. So here you have here the staggered arrangement, and it's illustrated in figure 620 in your 8th edition of the textbook. So this is just a sketch now showing these offset by 1/2 of the tube spacing, right? They are not anymore aligned pretty nicely like in the previous image. Again, we need to define here the transverse pitch, and again, the transverse pitch of ST is the tube spacing perpendicular to the flow direction, and SL is the longitudinal pitch tube spacing parallel of the flow direction. Okay, so these are two common geometries or arrangements of banks of bundles that we can have. And equations to solve our two bundles we can find in our same table, the table we have been using for external convection. And I mark it here in pink, okay? So as you can see, we can have equations or the Nusselt equation for two bundles in cross flow for brands bigger than one being this equation. And if you see, we have again parameters. So if you can go to the table, you will see that we have C, N, and M parameters that we need to read from a table as we did for a single circular cylinder or non-circular cylinder. So very convenient, the table has here the parameter CMN table, but you need to choose this CMN parameter table depending, as you can see, on the Reynolds, the geometry, if it is in line, if it is a stagger, if it is in line, and the ratio of the pitches, transversal to longitudinal pitches, okay? So it's something you need to be very careful when working with this table, because you need to choose the C and M parameters depending on the Reynolds, the geometry of the bundle, if it is in line or stagger, and the ratio of the pitch, longitudinal to transversal pitch. So we have here again, then for if you have flow over stagger to bundle gas or liquid metals. So you have two other relationships of the nozzle depending on what's going on there in the bundle. So today we are going to solve a problem using this section, this table, so you can see how to solve for a bundle. Very important that you should realize at this point, the Reynolds here that you need to use for solving for a bundle or tube bank is based on the maximum velocity that occurs in the tube bank. So before calculating the Reynolds, you need to determine the maximum velocity in the bank, okay? Because you will then use that U max to get the Reynolds max. And this is like a little algorithm that will help you to determine that maximum velocity. And this algorithm, if you can have it handy in your equation sheet, that could be great, because that will help you a lot to determine that U max to get the Reynolds max. So let's look for inline, the first geometry. So in the inline arrangement, the maximum velocity of the bank occurs at the transverse plane. Then you calculate U max with this equation, okay? U max is the transversal pitch divided by transversal pitch minus diameter multiplied by free stream velocity. So inline is straightforward. What happened with the stagger? With the stagger, you need to decide how to calculate that U max. So in a stagger geometry for a tube bank, U max occurs as the transverse plane, P1 or P2, depending on the spacing. Then you need to calculate first this SD, that is the tube spacing parameter, okay? Then compare the SD versus transversal pitch plus diameter divided by 2. If SD is less than the average of ST plus diameter, if it is less, you calculate, yes, it is less. Okay, I'm going to calculate my U max with this equation, where SD is defined here in terms of the transversal and longitudinal pitches. If SD is no less than this average, then you calculate U max as an inline arrangement, right? Okay. Also, when dealing with tube banks, we need to add correction factors. And we have to account for correction or include these correction factors if we have less than 10 rows in the tube bank. So this is a correction factor. Here, this table 6.3, that accounts for fewer than 10 rows in the tube bank. So if we have less than 10 rows, we need, as you can see here, is 10 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows. And depending on the geometry, the stagger or inline, we can read here a correction factor for accounting for these small beds or small banks. So table 6.3 is another important table. Other important equations that are within the chapter are these two equations for banks. And the first one, typically we use it to calculate the outlet temperature. Since typically the tube surface and inlet fluid temperatures are known, this relationship is typically used to find the outlet temperature of the bank. Like, okay, I'm going to pass nitrogen at 200 Celsius through my bank. How much is going to be the nitrogen temperature at the exit of the bank, right? This equation helps us for that. Where the big N is the total number of tubes in the bank, and NT is the number of tubes in a given row. So we want to know T naught or T outlet because we will know T initial, the T wall, right? The diameter, the total number of tubes in the bank, the age, what else? Density, free stream velocity, the pitch we can know, right? Because we know how to arrange our tube bank and the CP, heat capacity. Very important to have in mind at this point, and we will carry this equation until heat exchanger, is that as the fluid flows across the bank, the temperature change significantly from the free stream temperature. Then the correct approach for calculating the temperature differences in banks and in heat exchangers is the log mean temperature difference. You cannot just make an average. You cannot just say T initial plus T outlet divided by 2. No, because we have a 2D arrangement. We have a bunch of tubes. So we have different profiles of temperatures there happening. So in order to approximate the average temperature occurring in the bank, we use the log mean temperature difference, okay, that is given by this equation, where TW or TS is the tube surface or wall temperature, TI is the fluid inlet temperature, and T naught is the fluid outlet temperature. So again, for two banks, you cannot just give the average temperature occurring in the bank. You need to get the log mean temperature difference. So let's solve for a bank. And this bank is in your textbook. You can find it there. So let's see how to use all the equations. Just as preheating air improves combustion efficiency, so does preheating the fuel. For a typical furnace, methane gas at 20 Celsius is to be preheated in a heat exchanger consistent of a staggered arrangement, so we know that is a stagger, of 4 centimeters outer diameter, 5 rows in depth, with a longitudinal spacing of 6 centimeters and a transverse spacing, so these are the pitches, right? 8 centimeters, see the figure. Subatmospheric pressure steam is condensing inside the tubes, maintaining the tube wall at 50. Determine first the average heat transfer coefficient for the tube bank, so the H value, and then the pressure drop through the bank. The methane flow velocity is 10 meters per second upstream of the tube bank. So essentially, we are dealing with our first heat exchanger, as you can see. We are just evaluating the fluid outside the tubes, right? So we can get methane properties from table 36, appendix 2 in your textbook at a bulk temperature of 20 Celsius. So if you go to that appendix, you should be able to read the density, thermal conductivity, kinematic viscosity, and the brands for methane at 20 Celsius. Then at the surface temperature of 50, we read the Prandtl surface because we will need the Prandtl surface, 0.73. Hence, if we make the ratio prand versus divided by prand surface, we will have 1. So the prand equals the prand surface. From the geometry of the bundle, we see that the minimum flow area is between the adjacent tubes in a row. That is the half the frontal area of the tube bundle. Then the maximum velocity is 2 times the velocity of the methane, that is 20 Celsius. I mean, you can realize that if after, some practice with tube bundles, but if not, you use the algorithm I gave you, okay? So I'm going to use the algorithm here to double check it is 20. So I'm going to get SD, right? And then I'm going to compare SD versus the average of transversal pitch times diameter and decide which equation I'm going to use for Umax. That was the algorithm, right? So let's calculate SD. So as you can see, here the equation is corrected. This little 2 is inside my square root. So longitudinal pitch, 6 centimeters squares, plus transversal pitch, 8 centimeters divided by 2 square, and a square root of all of that. So step by step here, right, I got the square root of 52. Square root of 52 is 7.21. Now I'm going to apply the little algorithm I showed you in the previous slide. SD is smaller than the average of ST plus diameter divided by 2. So this 8 plus 4 divided by 2 give me 6. So 7.21 is smaller than 6? No. Then I'm going to calculate Umax with this equation. And you can go back to the algorithm to check that. So then Umax can be calculated by this equation, ST transversal pitch divided by transversal pitch minus diameter multiplied by the free stream velocity, that is 10. So 8 divided by 4, 2 times 10 gives me 20. Okay, so that's how you can apply the little algorithm I gave to you in order to find the maximum velocity in the bank, so then you can get the Reynolds number. This kind of approach that your book gives here, I think is doable. Like once you get more practice with tube bundles. For now, I think the algorithm becomes pretty useful. In the meantime, you get some practice. Okay, so now that I have the maximum velocity occurring in the bank, I want to know the Reynolds to determine the regime, right? And can get my nozzle equation properly out of the table. And then with that nozzle, get convective heat transfer coefficient. That is the first answer this problem is requiring, okay? So the Reynolds max is calculated then with the maximum velocity in the bank that we just get, multiplied by diameter, divided by the kinematic viscosity for the methane at 20 Celsius that I just read from my tables. That gives me a Reynolds max of 49,170. Besides the Reynolds, I need to know the ratio of transversals to longitudinal pitch to go to my table and choose the right nozzle equation. So ST, or transversal pitch, divided by longitudinal pitch is 8 divided by 6. That is going to be less than 2. So this could be my equation, right? This would be the equation I will be using. I have the Reynolds number within that regime, and I have the ratio of transversal to longitudinal pitch less than 2. So my C parameter is going to be 0.35, my M parameter is going to be 0.60, and my N parameter is going to be 0.2. So I take this equation. This equation is how it's presented in table 6.6. I just rearrange it for the nozzle. So I just put the nozzle to the left side of the equation and the rest to the right, right? And I have the values of ST, of the pitches, transversal and longitudinal. I already read the values for C, for N, and for M according to the Reynolds. So this would be in numbers, my nozzles equation. That would give me 216 nozzles. And now out of the nozzles, I can get the convective heat transfer coefficient. If I want to know the heat transfer rate, then I just plug, right, that H value times the area, the surface area, but not only for one tube, you need to consider all tubes, times delta T log mean difference. But the problem in this case just asks for H. Since we have 5 rows, that is the less than 10, we need to apply the correction factor in figure 6.3. So 1.79 times my correction factor, I have 5 rows and I have a stagger. So my correction factor is 9.92. So it's what I did here, 0.92 times H. The next question is, what is the pressure drop in the tube bank? And we have this equation given in your textbook. And so we need to read a figure that is figure 6.24. So if you can go to the figure 6.24, that will give us a correction factor depending on the pitches and the Reynolds number. So we know the Reynolds number, and we know that ST over SL, or the transversal divided by the longitudinal pitch, is 1.33. So with the Reynolds is this plot, 4 point something, 10 to the 5. I can look at the number here. And with the transversal pitch less than 0.2, so less than 2, sorry. So this is 2, and this is the line 1.5. We are in less than 2, and the Reynolds 410 to the 5, right? We can locate this point for the pressure drop coefficient for staggered banks. You will have a similar plot in your textbook for inline banks. We are reading the pressure drop coefficient for staggered banks. Okay, do not confuse those. So we can read a pressure coefficient of 0.25, right? With an X value of 1, according to the pitch, again, the ratio of the pitches, right? So again, we need to read this figure, this whole figure, for pressure drop coefficient for our stagger bank. You will have a similar plot, but for inline banks in your textbook. So with the Reynolds, the ratio of the pitches here, that is less than 2, we can read 0.25 of Fx of the pressure coefficient, but we need to know how much is X. And to know how much is X, we use this little inset here, okay? And in order to read this little inset here, we need to know the Reynolds, right? And the Reynolds, we are in 10 to the 5, right? So 4.9, 10 to the 4. So 10 to the 4 would be here. ST over SL was 1.3 because it was 8 divided by 6. So we are here. We go all the way to the left, and we get 0.25 Fx, right? But we need to know how much is that X, so we can just have the pressure drop coefficient to put into our equation. So the Reynolds is here, the ST over SL is here, so the X is 1, so 0.25 divided by 1. That will be our friction or pressure drop coefficient for this bank. So this is the 0.25 from that table times the density multiplied by maximum velocity occurring in the bank square, multiplied by the number of rows, we have 5, divided by 2 GC, the GC conversion factor. And this is equation 6.34 in your textbook. So we have a delta P through the tube bank of 167 Newton meter square. So again, what you need to solve for this is just this F, the friction coefficient that you get from the figure. Be careful when solving problems for tube banks. We have figure for a stagger and we have figure for inline. So as you can see, the solving for a tube bank requires A lot of tables, a lot of time. If you do it from scratch by yourself, it's a lot of time. And you should be very careful in choosing the nozzle equation, the nozzle parameters, um, and reading properly the tables and the charts. So let's evaluate now pack bets. And these pack bets are going to become very important for your reaction design course because the pack bets are one of the most common industrially employed uh, geometries for reaction. Um, so these pack beds are typically used in processes that require contact between a gas or a liquid stream and solid particles. They allow transfer of heat and or mass between the fluid and the particle. Uh, Obviously, in this course, we are going to evaluate only the transfer of heat. Once you reach your next semester reaction design, you will evaluate now the mass transfer. So examples, catalytic reactors, beds for storage of solar thermal energy, gas chromatography, and desiccant beds. Depending on the use of the pack bed, it might be necessary to transfer heat or mass between the particle and the fluid, or it might be necessary to transfer heat through the wall of the container vessel. So that depends on the application and the use. So here is an image you have in your textbook for a typical pack bed heat exchanger. And for the case of heat exchangers, these are common packing geometries that you have available commercially, such as the steel pole rings, steel rushing rings, or the ceramic saddles. So those are common shapes for the case of pack bed heat exchangers. Again, we need to realize how to calculate the Reynolds number. As you saw for two bundles, the Reynolds number the calculation becomes different because now we need to know the maximum velocity in the bank. Well, here in pack beds is going to change also how we calculate the Reynolds number. Because the presence of the catalyst particles or the packing modifies the wall heat transfer to the extent that the correlations through an empty tube are not applicable. Then correlations for mass and heat transfer in pack beds use a Reynolds number based on the superficial velocity. So we are using superficial velocity here to evaluate the Reynolds, or the fluid bed that exists if the bed is empty. The length scale to evaluate the Reynolds and the nozzles now is going to be the diameter of the packing. So again, for the Reynolds, we are going to use the superficial fluid velocity to get that Reynolds. And the length scale employed in the Reynolds and the nozzle is going to be now the diameter of the packing. Since not always we have spheres, an equivalent particle diameter that is based on the volume and surface must be defined. So that will change with equation, as you will see later. Another important parameter for beds or packed beds is the void fraction, which is the fraction of the bed volume that is empty, or 1 minus the fraction of bed volume occupied by the solid. That's epsilon, the void fraction. Okay. So these are just parameters that you need to have in mind when evaluating pack beds. Again, Reynolds based on the superficial velocity. The length scale now is the diameter of the packing, and sometimes we need to calculate an equivalent particle diameter, since not always we pack spheres like you saw in the previous slides, right? We have rings, for example, or more complicated geometries. Another important parameter we might not need to know is the void fraction, that is 1 minus the fraction of the bed occupied by the solid. And that you will employ a lot in, again, your kinetics course. So let's go to the correlations, and you have these correlations in your book. I took directly these from your book. And the first equation to evaluate pack beds is the Whitaker correlation for heat transfers from gases to different kinds of packing. and it's this equation, equation 6.41. So if you want to open your book and check equation 6.41, the Whitaker correlation for heat transfer from gases to different packing from several sources. What are the packings included to evaluate this equation? Cylinders with diameter equal to height, spheres, and rushing rings, partition rings, and Brill saddles. So the range of Reynolds and Boyd fraction, you can use the Whitaker equation is given here in your textbook. And Whitaker defined the packing diameter as 6 times the volume of the particle divided by the particle surface area. So that would be your dp, or diameter of the particle. And Whitaker defined the Reynolds number with this equation. So all of these equations were developed by Whitaker and help us again to get the heat transfer from gases to different kinds of packing. But as you can see, the nomenclature completely changed at this point. We calculate the Reynolds number in terms of the diameter of the particle, that is 6 times the volume of the particle divided by the surface area, and we calculate our Reynolds number employing also the Boyd fraction here. Another important equation is the Upadhyay mass and transfer analogy, and you have it here in your book, equation 6.42. And it's recommended to study heat and mass transfer in packed beds at very low Reynolds number. So the Reynolds range is between 0.01 to 10, right? And knowing the Reynolds, right, in the brand, you can get H out of here. In the range of 10 to 200, the Reynolds number is defined by this equation, where the partial diameter or the particle diameter dp is AP over pi, where AP is the particle surface area. The range fraction, the range Boyd fraction tested by Upadhyay was fairly narrow, and the data were only for cylindrical pellets. The actual data were for mass transfer operation, dissolution of the solid particles in water. Use of this correlation for gases, Brandt equals 0.1, may be questionable. So you need to be careful with that. For gases, or Brandt 0.71 might not give you pretty nice results because the way the experiments he conducted. He employed dissolution of solid particles in water. So the third correlation, so again, equation 642 and 643 in your textbook. The third correlation important for packed beds is the Beek correlation. So it helps us to compute heat transfer from the wall of the packed bed to the gas. So this would be our equation that we will be using to get HC, or convective heat transfer coefficient. For particles like cylinder which pack next to the wall, we use this one. For particles like spheres which contact that wall at one point, the Reynolds number is given by this equation, where dP is defined by Beek as the diameter of the sphere or cylinder. For other type of packings, a definition such as that by Whitaker should be suffice. The properties in these equations are evaluated at the film temperature, that is the average of the surface plus the free stream. And also he provided us a friction factor correlation, where delta P is the pressure drop over the length of the packed bed. So as you can see, the Beek, the Whitaker, the Upadhyay equations should be used very carefully, guys, because they were developed for specific situations, right? And each of them define the diameter of the particle differently, sometimes the Reynolds, based on the experiment. Like Upadhyay, you cannot use it for gases, or if you use it for gases, you have to be careful with the type of answer you will get, because might not be that reliable since he did his experiments using a liquid. So that's what we have so far for pack bets, these three correlations. So if you want to mark them in your book, they are there in your book. So you be careful when using one or the other and the nomenclature employed. So packed bed heat exchangers, often called packed bed reactors, reformers, or absorbers, are extensively used in chemical, petroleum, and power industries. In one such application where non-reacting tubular system is employed, so no reaction, so that simplified stop is only heat transfer. Carbon monoxide is to be heated from 50 Celsius to 350 Celsius in a packed bed. The bed is a pipe with 7.62 centimeter inner diameter with a random arrangement of solid cylinders of 0.93 centimeters in diameter and 1.17 centimeters long. The flow rate of carbon monoxide is 5 kilograms per hour, and the inside surface of the pipe is held at 400 Celsius. So those are here in the drawing here. And actually it's example 6.6 if you want to follow it in your textbook. Determine the average heat transfer coefficient at the pipe wall. So we want to know that the average heat transfer coefficient at the pipe wall. So that means that we are going to use Beek equation because Beek equation is a correlation that helps us to evaluate the heat transfer from the wall of the packed bed, right? So as established by Beek, we need to get the film temperature. And the thin film temperature at the inlet is 400 plus 50, and at the outlet is 400 plus 350. So then we evaluate the CO2 at the average of these two, T-film inlet plus T-film outlet divided by 2. This is because we have two different temperatures, inlet and outlet. Typically, we are just given the inlet, but this problem provides us two, so we can get the field temperature at 300 for CO. And you have table 30, appendix 2 in your 8th edition of the crate, so you can read for CO2 at 300, kinematic viscosity, thermal conductivity, density, heat capacity, and the prance. The superficial velocity is going to be the mass flow rate divided by the density multiplied by the area. So that gives me 18.27 meters per hour. So this equation, we have it, the superficial velocity, we have it there on the top of the previous slide or in your textbook. Is nothing more than mass flow rate divided by density and multiplied by the area. Besides the superficial velocity, we need to calculate the Reynolds at the diameter of the particle, because we said that for packed beds, we are using now the diameter of the particle, right? Since we are using Beek equation, we need to see what Beek defined it as the diameter of the particle, because remember each one defined the diameter of the particle differently. So Beek define dP, or the diameter of the particle, as the diameter of the sphere or the cylinder. So we have that straightforward. Our diameter of the particle is going to be 0.93 centimeters, or around 1 centimeter, 0.01 meters. The Reynolds with now this particle diameter can be calculated. Here, don't forget, just for homogeneity, I'm multiplying here to have everything in seconds and remove the hours, right? Because I have here the kinematic viscosity in seconds. So just for homogeneity. And I get a Reynolds of 100.5. Using the Beek equation for computing heat transfer from the wall of the packed bed, we have this equation, we have the Reynolds, we have the Prance, so we have everything. So we just plug numbers and get an H of 14, H times dP over K of 14. So in order to just have the H or convective heat transfer coefficient, I'm going to multiply this H by K and divide it by dP, because that's what the equation shows here, right? So I get a convective heat transfer coefficient of 60.1 meters squared Kelvin. So again, this is an example in your textbook. You can follow it there. And the only thing with pack beds is that you need to check what the problem is asking. So here it asks us to evaluate the heat transfer at the pipe wall, and Beek is the one that gives us that correlation, right? So then you go for Beek, and you just check how he defined the Reynolds, the diameter of the particle, and even if you need to calculate the friction factor, you can do it with this equation, because he provides an equation for that. This is from the wall. That's why we decide for Beek correlation. The other correlation help us to study the heat transfer or mass transfer at pack beds in the pack bed, not through the wall, right? So this won't help us, the update. And the same thing with the Whitaker. It is the heat transfer from gases to the packing. So that was one helpful. So that's the first step, to realize which of the three you are dealing with. Then choose your equation. Be very careful how each author defined the Reynolds, the dP, and everything, and just apply the equation.